Hi, Ryan here. Today we're going to be learning about forces. I've promised to make this video for a while. Sorry it's taken a bit of time. This is going to be the first video. It's going to be an introduction to forces, what they are, Newton's three laws, the kinds of forces you're going to be dealing with at the beginning in this class, and a bit on free body diagrams. The second video will cover how we actually apply all of this to solve various force problems. With that, let's get started. So a force is simply a push or a pull. We have specific units for forces. They are newtons, symbolized by a capital N. By the way, any unit named after a person will be capitalized in its abbreviation. So kilograms are not capitalized because their grams aren't named after a person, but newtons are. The Newton itself can be broken up into fundamental units of mass, length, and time squared. You don't necessarily have to memorize this. What you will typically do in an intro class is associate a particular unit with a quantity and an equation for which you have memorized. And you can use that equation to derive the fundamental units if necessary. So Newton came up with three laws governing three laws of motion, and they govern forces. Newton's first law can be abbreviated with a single word, inertia, and it reflects the resistance of an object to change. In this specific case, it's going to reflect its resistance to changes in velocity. An object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by a net external force. So what this means is that if we don't have a net force, or no forces at all, the velocity will be constant. This does not mean the velocity is zero unless the object's at rest. So that's going to be important. Remember, a net force just means the velocity is constant, means no acceleration, but it doesn't mean no motion. So what if we do have a net force? If we have a net force, some are written by a sum of forces here, that's going to translate to an acceleration depending on the mass of the object. The larger the mass, the less acceleration it will have. So sometimes this is written as acceleration is proportional to the net force and inversely proportional to the mass. So mass is this idea of inertia, this resistance to change. The more mass an object has, the more resistant it is to change. We're going to be using this equation all the time in this class. It is perhaps the most important equation in physics, far more important than E equals mc squared. In practice, because this is a vector equation, we're going to be breaking it up into components, typically just in the x and y, but you could also do it in the z direction. And we translate this vector equation into a scalar equation where we actually add the magnitudes of the forces in the x direction, keeping track of their direction with minus signs as needed, equals mass times acceleration in the x, and we do the same in the y direction. This is how we will solve most of the problems in this section. The third law is action-reaction. So the phrasing usually goes, for every force there is an equal and opposite reaction force. Now, there's actually quite a bit of detail and subtlety in this, and so I'm going to take a little bit of time to talk about that. So action-reaction basically says that forces are the interaction between two different objects. And that interaction is going to be come in pairs of the same type. So an action-reaction pair will never be of two different kinds of forces. It won't be a normal force and gravity. It has to be two gravitational forces, two normal forces, two friction forces, etc. Each force acts on a different object. So you have two forces that are equal and opposite but acting on the same object. They can't be an action-reaction pair. It's always due to an interaction between two objects, so those forces are acting on each other. And the forces act in opposite directions. So as a quick example, if I have a block and the Earth here, that block will be have a force of gravity exerted on it from the Earth. So I'll call that block on Earth, or sorry, Earth on block. These forces have to come on pairs. There has to be an equal and opposite force of gravity of the block on the Earth. So it may seem wild to think that the block pulls just as hard on the Earth as the Earth pulls on the block. But that's true. Our intuition feels like it should be weaker on the block than the Earth, but that's because the block has less mass. And so even though the forces are equal, the acceleration will be very small on the Earth. So this block, if it's falling toward the Earth due to acceleration from the force of gravity, the Earth is actually falling up toward the block, just at a minuscule rate. So we have several kinds of forces that we're going to be dealing with in this class. The first force we'll talk about is gravity. It's a fundamental force. Near Earth's surface, or near the surface of any object, the force of gravity will be approximated very well by the mass of the object near the surface times the acceleration due to gravity near the surface. So for on Earth, that's 9.8 meters per second squared. The Moon, it's 1.6 meters per second squared. Just whatever local gravity is near the surface of that object. Once you start dealing with distances that are farther than near the Earth's surface, you're going to switch to Newton's universal law of gravity. It's got a formula that's a little bit more complicated. I'm not going to go into tons of depth here, but it's equal to the gravitational constant, big G, 6.67 times 10 to the negative 11th in MKS units. The product of the masses, so if you're talking about an object near the surface of Earth, M1 might be the mass of the object, M2 might be the mass of the Earth. The order in which you do these does not matter, because again, they're interacting forces, and the force is going to be equal, divided by r squared. R is the distance from the center of one object to the center of the other. So if you're doing an object resting on the surface of the Earth, r will simply be the radius of the Earth, because this distance is very small. But if you're dealing with an object that's traveling some distance h above the surface of the Earth, r will be the radius of the Earth plus the height of the object. So do be mindful, it's from center to center. This object is fairly small, so this distance from the edge of the object to the center would usually small. But if you're dealing with two planets, then you have to factor in not only the separation distance from the surfaces, but the radii of each of these to get the total r, from center of mass to center of mass. We're going to be dealing mostly with this near Earth's surface, so it is important to remember that force of gravity is always acting down. The normal force, normal in math and physics means perpendicular. And there is a force perpendicular to solid surfaces in contact. So if I have an object that's sitting on Earth, the thing that's keeping that object from just falling toward the center of the Earth is something here on the surface. It's going to end up being due to the electromagnetic force. The electrons in this solid surface are repelling the electrons in this solid surface, preventing them from passing through each other. So basically the bonds formed in the solid lattice structure keep the electrons tight enough such that they don't pass through each other. Notice that if this were a liquid, it would be, the electrons are not bound as tightly, and therefore it would fall through the liquid surface. There's no formula for normal force. We end up calculating normal force by using F equals ma, plugging in other forces that we know, and solving for normal force. And normal force is important in calculating friction, which I'll talk about in a bit. It's always perpendicular to the surface. So here, normal force would be going up on this object. If I have an object pressed against the wall on the side, normal force would actually be going this way. And if I'm looking at an object at the top of a roller coaster, the normal force of the tracks on that cart would actually be going downward. So although you'll be used to normal force going straight up, keep in mind, and additionally, on a ramp problem, normal force will be going here because perpendicular to these surfaces in contact would be this direction. So be prepared to take a second and think about which direction normal force is actually going. Tension is the name that we give to force due to two objects connected by a string, a rope, a chain, something like that. Or an object hanging just from a string, rope, or chain. It acts from the endpoints inward. So the tension force due to this rope would be going from the endpoints inward, acting on these objects. They are equal at both ends of a taut string. So we're assuming in the vast majority of cases no flex in this. Otherwise, we'd basically model this as a spring. But assuming there's no flex, however hard the rope is pulling on this end has to be equal to how hard the rope is pulling on this end. This will also be true on either side of an ideal pulley, aka a massless pulley. This will change later in this class, but initially when you have a pulley system, let's say you have a block here connected to a rope that's hanging over the side, resting on this pulley system. Whatever the tension is here has to be equal to the tension here, as long as this is an ideal pulley. Once this is no longer an ideal pulley, these tensions will be different, although over this section, whatever the tension is here has to be the same here, and whatever the tension is here has to be the same here. But that's going to be much later once we deal with rotations. We also have the friction force. Friction is going to be always acting opposite the direction of motion or attempted motion. We have two kinds, static and kinetic. We're going to talk about kinetic first. It's a little easier to think about. So if I have an object that's moving on a rough surface, the roughness of the surface, the interaction of the electron repulsion between these two rough surfaces, is going to push against the direction of relative motion. So if this object is sliding on top, it's going to experience a friction force this way. Now let's think about action-reaction. Forces always come in pairs. So if my top hand is sliding in this direction and it experiences a force this way, I can feel that my bottom hand, even though it's not moving, because of the motion relative to between the two surfaces, is experiencing a friction force in the opposite direction. So if I show this on a piece of paper, if I have a friction force, let's say this thing is moving up here with some velocity v, and there's roughness between these surfaces. If I have a friction force acting this way from this rough surface, this is going to lead to an equal and opposite friction force here on the ground. Now usually we don't worry about the force of friction on the ground, but if in fact we have, instead of a block and the ground, we have a bunch of stacked objects, that may actually be very important. So we have a formula for the kinetic friction force. The kinetic friction force is going to be equal to the coefficient of friction times the normal force between the two surfaces of interest. So if we have stacked block problems, we have to keep track of which normal force we're talking about. For most problems, we're going to be dealing with a single normal force. For instance, the normal force on the block from the ground. This mu k is a coefficient of kinetic friction. It is dimensionless because that has units of force and that has units of force. This is something that you'll be given or occasionally solve for. Typical values range from 0.03 for like ice to maybe 0.3, 0.4 for rubber on pavement, stuff like that. There's nothing preventing it from being a number bigger than 1 other than the fact that most materials just don't have that much friction between them. Static friction is used if the surfaces are not moving relative to each other. So if I put my hands over each other and I try to slide my top hand but don't actually succeed, I still feel a force pushing backwards this way. And in fact, that backward force is just enough to actually keep it in place. So static friction force will be a little bit complicated, and as a result, we don't actually have an equation for it, we have an inequality. The maximum static friction will be equal to the coefficient times the normal force, but the actual static friction force will typically be less than that value, so we have to derive it again by setting our equations up and solving for it. Also, typically the coefficient of static friction is bigger than the coefficient of kinetic friction. Think of it this way, it's harder to start something moving than to keep it moving. I'm going to cut off the video here because we've got a lawnmower going off. I'll talk about free body diagrams and how to solve problems next time.